All right. Let's talk about reducing gRPC call volume through caching and bashing. So I'm Benjamin Fedorka. My pronouns are he, him, and I work on the Java platform team at Netflix. My team specializes in the experience for RPC-oriented APIs. We call ourselves the Baja team. That's backend application Java APIs. We deliver a consistent developer experience for point-to-point communication and JVM applications. We do this by providing a variety of RPC frameworks. We have Netflix gRPC Java, we have Netflix Web Client, we have our own little flavor of Spring MVC, we have our open source ribbon, and then my team also supports a variety of supporting tooling that we use to provide these frameworks. That's our OSS Netflix concurrency limits, our OSS Netflix historics, and then Spring Boot and Juice integrations. Netflix gRPC Java is our most highly featured and complex RPC framework. We have over 2,500 applications with gRPC clients, gRPC servers, or both. So it's critical that these integrations are easy. We call making things easy our paved road. We approach this challenge from 5 angles. Tooling, how do engineers send out ad hoc requests and actually author their protos? Security, how do we establish and enforce the integrity of our RPCs and provide additional access controls? Resilience, how do we ensure that RPCs succeed or degrade gracefully? Observability, how do we understand the behavior of the system? And then finally, ergonomics, how to make all of this easy? Last year, I presented at this conference a whirlwind overview of these pillars. You can find it on the CNCF and gRPC YouTube pages as how Netflix makes gRPC easy to serve, consume, and operate. Today, I'm going to dive into 2 ways we reduce our call volume while still successfully serving fully featured responses: response caching and request batching. Now, I want to highlight here, I'm really talking about how we get fully featured responses. We're not going to go into load shedding. We're not going to go into how our fallbacks work. This is how we make sure that all of our clients get the best response possible for their request. So caching expensive operations isn't a novel idea. We spend some memory on the client, server, somewhere else to reduce the need for limited resources. Now, most of us will probably have written something like this in the past, right? We have a cache, we compute something if it's not there. So if on a cache hit, we avoid that expensive computation. On a cache miss, we rewrite the response back to the cache and use it later. This is your basic read-through cache, and it works. So we do it again and again and again, and this is not a good developer experience. One of the pillars of our gRPC product is ergonomics. We need to ensure that normal activities for service owners and their client consumers are easy. So we can't just put a caching facade and set it in front of every RPC or in front of every proto service because you're doing a ton of work over and over and over again. So what if we did all of this and more just built into our server channels? So if we were to implement our caches within our client channels, they would be available to all of the different stubs. This means that we could add client-side caches without a migration because the APIs didn't change. Similarly, if we add caching into the server channels, we avoid calling that service implementation. This is possible by writing a unique caching interceptor for every client and service, and then when you build your channels, you just add that interceptor into the flow, but we can still do better. So let's back up. We're using Proto to define our services and to generate our low-level clients. Proto already has a stub, already has a method option for immutability built into the stubs. Can we go forward one slide? So Proto already has the immutability as an option in there, but we can put some additional method options in there for cacheability, such as are you cacheable, are you needing to evict on caching, or are you going to implement a write-through cache instead of read-through cache? So we express this now with the method option. So now that we have this in our server specification, we have the cacheability method as a core part of the RPC. So co-locating the information in a machine-readable format is perfect. So here we see we marked our RPC as cacheable, and we defined an optional cache key. Now, if you don't define a cache key, that's fine. We can generate one for you just by looking at the entirety of the request. But normally, you don't need every single field in your request as part of your key, and these friendlier keys are easier to operate. So these cache directives then get compiled into the stubs, and we can query the details at the channel creation time. So we use that information to build an interceptor, either client-side or server-side, which actually implements the cache. From a technical standpoint, the interceptor is going to capture the response handler and delay forwarding the call to the next interceptor until the client has sent the message and half close to the RPC. At this point, the cache is queried through a non-blocking API. On a cache hit, we take that response and we can pass it to the response handler. And then on a cache miss, we take our buffered headers and message, and we pass that along to the next interceptor and eventually transport. When we get the response back through our interceptor, we can put that into the cache. If the proto-based configuration is insufficient, we actually have a lot of customizations that we make available. So we allow our services and clients to inject custom code for determining cacheability, cache keys, eviction rules, or even the entire cache. Now you might wonder, why would I want to replace the entire cache? Why would I just not do it myself? And the reason is caching integrates with a whole bunch of other things. We have our basic implementation of the caching interceptor, but we also have integrations with our observability. We need to know how well caching performance is happening. We don't want to break our latency reporting based on caching. So we encourage our customers to integrate against our caching APIs instead of writing their own caching interceptors. A great example of when you might want to make a completely custom cache is if you could support multiple RPCs through a data transform, or if a RPC cacheability might change based upon the presence of a field. Diving a little bit deeper on configuration, we've done a lot of ergonomic work here. So when fields are not present, we allow configurable default values so that we don't just get empty blanks or maybe a double hyphen in your cache key. Not shown here, cache keys can descend into child messages via dot notation. This makes for really concise looking keys without having to write custom code for figuring out what your cache keys should be. And RPCs can evict entries written by other RPCs. So as an example, if you have a gRPC service that's doing both reads and writes, you can automatically have the writes evict all of your reads, and that way you can keep that data a little bit fresher. What we don't do in the proto level is configure specific caches or TTLs. These values tend to be client dependent. We don't know what caches are going to be available on the clients, and we don't necessarily know what data freshness every client needs. So what we do instead is we pack that information into our standard configuration service. Our service owners configure default values, and those get distributed out. And then individual services can override these at runtime with their specific needs. Client-side and server-side caches both respect HTTP headers for cache control, and caches responses served from caches are going to include metadata for debugging purposes. This is going to make it really easy. We still look like we're an HTTP caching service, even though we implemented everything custom. So taking all of this together, we've got interceptors in both our client and server channels, which automatically wire in the caches as needed. Because we implemented caches at a channel level, it's already working with all types of stubs. We didn't change any APIs, so a service owner can add a cache without having migration, and this new capability just gets rolled out across the fleet with dependency updates. The caches even work with facades created by service owners because those facades are calling our stubs underneath. Let's take a moment to acknowledge where caching doesn't work. The first one is streaming calls. Honestly, we haven't found a good user story for needing this. Everybody who needs streaming calls doesn't need caching. If you have a case where you're using caching with streaming calls, or you might think that would work, I'd love to hear about it over lunch. The other thing that you need to be really careful with is out-of-band information. And a great example here is the security context. So if you're integrating with the cache, you need to make sure that you're still taking the security into mind. Is the caller that, does the caller have access to call the RPC? If it doesn't, it probably shouldn't have access to the cache. Maybe you're doing field level validation against security, so you might return different visibility for different colors. You need to make sure that that's accounted for outside your caching layer, or you need to not be using the cache for that. Very similar is field masks. If you were to cache a response with some hidden fields, is it still correct for those other colors? So these are some things that you have to think about. And notably, this is all out of band with the proto specification, and that's what causes these difficulties with caching. So we support several flavors of caches depending on the client and server capabilities. Client-side caches are extremely low latency and easy to configure. We have both on-heap and off-heap caches for our Java services. And we have an extra cache which is implicitly keyed per incoming request. We'll talk a little bit more about that one in a little bit. Server-side caches are our last line of defense before investing in a potentially expensive computation. Just like client-side caches, our server caches are enabled via the proto specification. A natural extension would be to run both a client-side and a server-side cache. But instead of doing this, we use our open source EV cache and run a distributed cache that's shared between both clients and servers. So we've got some cache on servers, some cache on clients, some cache sitting outside, and it's replicated through all of them. So with all this effort to make caching easy to integrate, and the efforts from our cloud engineering team to provide caching behavior just to begin with, how well does this work? So this is actually a fleet-wide view of our gRPC client caching performance for Java services. On average, we're seeing 75% of stub invocations are served by a cache. So we actually only have to run our gRPC servers for 25% of our overall traffic. So let's dive in on a specific service. We run a lot of A/B tests to ensure that we're providing the best experience for our subscribers. This means that services frequently need to check which feature flags should be enabled for a particular incoming request. It's common for these flags to be added throughout already existing services, and the flags are going to have different but predetermined values for each incoming request. By providing a cache which is implicitly scoped to an incoming request, engineers can inject the client for the experimentation platform wherever it's needed. The results will be cached for the duration of an incoming request and automatically evicted at the conclusion. And we can see that here, that big green section, that's all the calls that are served by just repeated calls into that request scoped cache. We also have layered caching here. So if the call was to fall through the request scope cache, then it's going to go into our distributed caching implemented by EV cache. So that means that only 5% of the requests reach the gRPC server. And even some of those are now served by a cache. So with a few lines of configuration in their service definition, this team avoids tens of millions of calls per second, and they didn't have to write a caching facade. It's just here. So a few years ago, we encountered something where caching wasn't enough. Many of you are going to be familiar with this view. It's the customized content recommendations we provide for every member. Once we know which titles to recommend, we still need to decide which art to display for that title. This logic was originally implemented in a library and called for many applications, each making many calls per incoming request. So even with this small screenshot, there's 18 different titles on the screen. So when we started working on deconstructing this monolith, we took the library and we re-implemented it with a microservice. And now this has created a huge fan out. Here's a simplification of that call pattern. So even with asynchronous requests, the image artwork service was getting a huge number of requests. It's getting 18 requests per incoming call. Refactoring the intermediary service was a large investment and would have delayed our efforts to retire library, right? We've got dozens of applications that are calling this library inefficiently. We don't really want to rewrite all of them right now. So it really shouldn't be a surprise how we solved this problem because it's the title of the section. We did it with request batching. So within each client, we intercept the stub invocations and aggregate them into a single call with multiple IDs for the title artwork. Once we received a response from the image artwork service, we slice it back into individual response objects and send it onto each stub. So filling in some technical details, in each call, we're going to capture that request object and the response listener. We're going to batch calls together based upon if they're made close to each other in time, looking at overall batch size, and other distinguishing features. Maybe we need to aggregate calls for a particular device type differently than calls for a browser. And then eventually, we send this on to the backend service as a single call. So for each request, we're going to save a key to help us identify that relevant data in the response. So when we get that response back, we can use those saved keys to identify what aspects of the data needs to go into each stub invocation. We slice that back up, and then we can call each response listener with the response. Now, in practice, this is not in proto. It's about 100 lines of manual code for every RPC that needs batching. Our framework does handle detecting that these batches exist, and we get those integrated with our essentially distributed interceptors and also wired up with all of our observability tooling. So as much as we've simplified it, it's still complicated. We need to think about how much latency do you want to inject into the call to reduce your batch size. So we are now possibly degrading that experience to reduce your requests per second. We also need to think about how we're keying these requests. If you were to add a field to your request object, that's probably going to ripple into code changes for your batchers. And then finally, All those considerations that make requests hard to cache, they still apply here for batching. Anything that's out of band with the request adds additional complexity for your batcher. So caching was a huge percentage of our traffic, and batching is a lot less. If the batch traffic is not zero, it's 0.007% of our overall traffic. And in fact, as of today, we only have one application to service connection still using batching, and that traffic is only 3% of that pair. So why aren't we using batching right now? Let's think about why we brought this capability in. The underlying services were using inefficient call patterns, and rewriting them would delay other goals. But that was 6 years ago. Today, almost all of these services have been rewritten. Batching allowed us to pursue other priorities at the time, and over the years, we eventually addressed that tech debt and drove it down, and now it's not needed anymore. So we expect to retire the last instance of request batching later this year. And we're going to simplify our stack by transitioning this from a required feature to an optional feature. So it's not going to be brought in by default anymore. If you want to bring in request batching, we're going to have to add that into your service. But keeping the code around just in case we need it in the future, who knows what might come up. So in summary, make request caching easy. If it's easy for your engineers to cache, they'll use it. And then if you need it, use request batching to fix the call patterns without refactoring. And I have now rushed through my slides, which is great because we have 12 minutes for Q&A. So there is a room mic, so if you have any questions, grab a mic.
So do you have a requirement on sharing the cache among your clients or the server? I guess the caching is good, to improve the performance, but at the same time, usually is local, is on its own instance, right? Usually, its own memory. So any requirement to share the cache among all your clients? Same kind of clients, multiple instances?
We don't have a requirement. A lot of our caches are local. So the caches that are local on the client tend to be lower latency. So we're looking at tens of microseconds of latency for those responses. When we are using distributed caches, which is going to help if maybe you have much higher magnitude number of client servers, or maybe they're cycling faster, then we'll use that distributed caching, but then we're looking at hundreds of microseconds for responses. So we tend to use it when needed.
Did your batching solution leverage your caching solution as well?
That is a great question. So it's difficult to have both caching and batching running at the same time because you need to decide which order they go in or try to do it on both sides. So ultimately, we were not using caching with our batch calls. So we had attempted to cache the calls individually first, and then if they didn't, then they fall through into the batch. Once you build the batch call up, there are so many individual request IDs, it's unlikely you're going to get cache hits. But if you put the cache on the other side of the batch calls, then you introduce a lot of complexity for how you actually build up your batches.
Hey, as a cache is so easy to be implemented, you talk about the security on the client side. I mean, how do we ensure the security?
Yeah, so the first level is if your client doesn't have access to the service, it shouldn't have access to the cache. So this really only applies for distributed caches because the other caches are going to be local to your client. When you're looking at per call security, so this might be if you have a client that's operating with multiple security contexts, maybe you're passing through an end-to-end user identity or something like that. That's that complexity where I talked about where you have out-of-band information, and you need to make sure that either it doesn't apply for your caching or that you have it integrated with your cache keys.
Can you talk more about the logic building batch? Kind of waiting for a next response when to decide the batch is ready?
Yeah, so we normally look at two things. We look at how much latency we're willing to introduce, and then also how many items are already in the batch. So the goal of batching is just to reduce the overall RPS going to the downstream service. So often, like if we already got 15 or 20 items into the batch, it's probably worth sending the batch off now to keep that tail latency low because we've already done enough to reduce the fan out. And both of those are configurable within the batcher, so we can continue to tune those as the service call pattern changes.
Yeah, I'll extend the question I have. So I have an existing service, already has security in place. I'm onboarding cache distributed. So do I need to implement the security on the cache again? I mean,
So it depends if it depends on how that security context works. So as an example, so we run mutual TLS identities between all of our clients and servers. And if that's the only thing that you're worried about, so service A is always able to call service B, then you don't need to think about any more security within your cache. It's really only if you're dealing with like end-to-end identities and you have a client service which is deputizing calls for other services, that's where you need to think about if your cache requires additional security.
Do you have any open source libraries available to help implement any of this?
That's a great question. No, we don't, and that's why I try to dive into some of the technical details so that way you can do it. And there's even some code screenshots in there. So there's an investment to get these libraries into open source, and we haven't been able to prioritize it.
So is your cache persisted at any time? What I'm trying to get to is usually these workloads tend to be ephemeral. So when we bounce these, the instances, the cache could be gone. So are you reloaded the cache? I mean, I don't know if you have intention to reload the cache from somewhere, or this is always started from fresh and constantly trying to build the cache along.
Yeah, so for those cases, that's when we use our distributed caching with our open source EV cache. So there is an instance which is sitting aside that can then load up a cache before the service starts serving requests. So for the caches that are local only, that are not using the distributed caching capabilities, they do start empty.
I see. Thanks.
All right, I'm going to say that we started or finished our questions early. And I know after me is lunch. So if you have any more questions, then find me.
So just to thank you so much, Benjamin.